Можно начинать, да? Хорошо. So, regarding the homework, only there were some problems only in the last problem on the homework. So let us discuss it briefly. So the last problem, so the first two problems were okay. The last problem was about the Riemann surface, hyperelliptic Riemann surface given by the equation by this equation. So we will consider this guy in C2, and then we know that it has a compactification, which is a compact Riemann surface of genus 3. Okay, and then problem was to prove that the automorphism group of this surface has order 48. Yes. Okay. Yes. Okay, so how to do it? So we have the projection, yeah, from x bar to CP1. And here we have points, the images of the Weierstrass points. Yes, so these points 0, plus minus 1, plus minus I, infinity. So these are, yeah, so these guys, 0 plus minus 1 plus minus I, are the roots of this polynomial. And all these points together with infinity, they are images of the Weierstrass points of the Weierstrass points. Yes, and then then the problem was then the solution consists of two steps. The first step is the following. So consider any automorphism of CP1, some phi, that preserves all these points. Yes, then phi can be lifted to an automorphism to some psi yes. Okay. Okay, then let us do it later. Okay, this is some general argument, but let us do it later. And then the step 2 is to prove that the number of automorphisms of CP1 that preserve all these points, so let us denote this set by S, so that the number of automorphisms of CP1 CP1 that preserve this set okay, strictly speaking, let us just prove that it's greater or equal than 24. Yeah, then I claim that these two steps are enough. Proof of, yeah, proof of 3. Yes, indeed. So if you have at least 24 automorphisms of CP1 that preserve this set, so all of them can be lifted to an automorphism of X bar. But you also have a hyperelliptic involution. Yeah, so here you also have a hyperelliptic involution that fixes all the Weierstrass points. So you obtain at least this number of automorphisms. So you are done. This is exactly what you want. Okay, so this is clear. Okay, then let us do these steps. Yes, step 2. Yeah, it's very easy. So you just what you do. So any point okay, let us so this set is S. Let us denote this group by H. So first you prove that H acts transitively. On S. Yeah, and then so this is easy. Yeah, so you just check that if you want to move 0, what to do? Yeah, so for example, you want to move 0. Yeah, for example, you want to move 0 to all other points. Yeah, so if you want to move 0 to infinity, then this is the transformation z goes to 1 minus z. Yes, so z goes to 1 minus z. It preserves this set, obviously, and it moves 0 to infinity. Okay, then you want to move 0 to, for example, 1. Yeah, then you apply the transformation z goes to z minus I, z plus I. To what you have, minus 1, yeah, for example. Minus 1. Yeah, and then again, it's a direct check it's a direct check that this transformation preserves this set S. Yeah. This set, yeah. S. S is this set. I. Huh? Что минус I? Один минус I. Нет, я хочу сказать, 0 переходит в минус 1. I want to move 0 to all other points. Yes. So to minus 1, and then obviously you can move all these points. Yeah, just by z goes to iz. Yeah. So if you can move 0 to minus 1, then you can move it to all other points. So H acts transitively on S, and then B, the number of automorphisms that fix 0, is at least 4. Yeah? Yeah, but this is obvious. Just these rotations. So you see that yeah. So the orbit of 0 consists of 6 points. So if you consider the action of H on S, so the orbit of 0 consists of 6 points, and the stabilizer consists of at least 4 elements. So it follows that the number of elements here is at least 24. Yes. Yeah, by the way, this is a quite beautiful picture related to this octahedron. Yes, some remark. What you can do? Actually, I think we discussed it in the spring course. So you can consider the sphere. The unit sphere. So these are x, y, z. Okay. The z actually, but okay. I think it's fine. So you consider the unit sphere. So this is unit. And you can consider the projection, stereographic projection. So okay, let us denote it by S2, this sphere. And you have stereographic projection from this point. Yeah, so you can yeah, maybe it should. Yeah, so you have the standard stereographic projection, stereographic projection from S2 to C2 union infinity. And then actually, then H, then this set. So here you have this set S, and then in S2 you will have vertices of octahedron. Octahedron. So they correspond. So if you apply the inverse to the stereographic projection, yeah, it's obvious. Yeah, you get these guys. They are exactly vertices of the octahedron. And then H, the group H is equal to the group of symmetries of octahedron. Actually, it's a nice fact that yeah. So this group is a subgroup in SO3. And under the stereographic projections, these symmetries of the octahedron, they give precisely Möbius transformations from this group H. Okay. Yeah, so this is step 2. And step 1 is...
But here we cannot represent the hyperelliptic involution, right?
Yes, yeah, this is exactly what it happens. So here we have at least 24 elements, but we also have hyperelliptic involution. So in total, we obtain explicitly at least 48 elements. But we know that there cannot be more. So we're done. Yeah, and step 1. Yeah, so you yeah, so yeah, for step 1, yeah, one can have some topological argument, but probably it's nicer to have just algebraic argument. Yeah. So what is the general argument? You have some hyperelliptic Riemann surface. Okay, Z minus Zi. Oh, maybe. Okay, Z minus Zi. And then you apply Möbius transformation. Yes. So and then you have the set S consists of the points z to j plus 1 infinity. And then you apply some Möbius transformation. Z equals az tilde plus b divided by cz tilde plus d. That preserves S. And then you want to check that it gives an automorphism of your hyperelliptic Riemann surface. But yeah, this is easy. So you just check two cases. Case 1, that infinity is preserved, is fixed. Is fixed. But then, if infinity is fixed, then it means that you have just linear transformation. Az tilde plus b. Yeah, and then you just substitute here. Yeah, so you so if you denote this as p of z, so you substitute, so you get p of a z tilde plus b. Yes, and then, okay, this is equal to a to the power 2g plus 1 times some p tilde of z tilde. Yeah, and then you just move to the left-hand side and you get y divided by a to the power g square root of a squared equals p tilde z tilde. Okay, and then you just denote this by y tilde. Yeah, so you get from yeah, okay, so your automorphism, so z is equal to this, and y tilde is equal to y over a square root of a. Yeah, so you find an automorphism of so you lift the automorphism of yeah, so yeah, and since yeah, so you have this linear transformation, and since it preserves all these points, then of course p tilde is equal to p. Yeah, and then yeah, these formulas define an automorphism of your of your Riemann surface. Yeah, and then the second case, yeah, okay, this is trivial case, and then there is there is the second case, case 2. So infinity is not fixed. Is not fixed. Okay, so it means that you have a general Möbius transformation. Z equals a z tilde plus b c z tilde plus d. And then you just what you can say? You can say that yeah, so you substitute. Yeah, so you obtain y squared equals p of a z tilde plus b divided by c z tilde plus d. this is equal to p tilde of z tilde over cz tilde plus d to the power 2g plus 1. Yeah, where this guy is a polynomial. Yeah, so this is a polynomial. Yeah, and then you note that you see you have an automorphism of this set S. So it means that in particular infinity, so A over C is the root of P. Yeah? A over C is the root is a root is a root of P. Yeah? Because this under this automorphism, if z tilde is equal to infinity, yeah, then z is equal to c. Yeah, and the infinity goes to some finite point. So you see that A over C should be a root of P. So it means that when z tilde is equal to infinity, this guy is 0. And then it means that this P tilde is a polynomial of degree 2g plus 2g. So a priori we have that it should have degree 2g plus 1, but actually the coefficient of z to the power 2g plus 1 vanishes. Yeah, and then you are done. You just then write. Then this is equivalent to you write y over c z tilde plus d. Yeah, and of degree 2g, and okay, I don't want to compute it, but yeah, suppose of degree 2g, and then the coefficient of z to the power 2g is let us denote it by some constant, some e, for example. Yeah, then you just write cz tilde plus d. You divide to the power g plus 1 times square root of e. I know what I want. No, I don't say. I want to move to multiply both sides. Sorry. So I want to multiply both sides by z tilde plus d to the power 2g plus 2. So I get y c z tilde plus d to the power g plus 1 squared is equal to c z tilde plus d yeah, then okay, here you want to divide by c times e. Then you want to divide here by square root of c times e. And this is your y tilde. Yeah, and this is now a polynomial of degree 2g minus 1. So it's let us denoted by q z tilde. And it should be equal to q of z is equal to p of z, actually. Or maybe I can just say this should be a polynomial p of z tilde, because it should have the same. It has the same roots. Yeah, so this is an explicit way to lift any automorphism of this set S to an automorphism of CP1. of your hyperelliptic Riemann surface. Yes, any questions? Okay, then we continue. Yes. By the way, what about homework? You stopped doing homeworks. Вы. Что насчет домашки? Вы что-то перестали делать домашку? Хорошо. Okay. Okay, so we continue the study of harmonic forms. So, yeah, it will be needed in Abel's, in the proof of Abel's theorem. So, so what we did, yeah, just very, very briefly. Yes, so if we have some Riemann surface and an open set, and you have some form, smooth form on U, then you can decompose it as a sum of a form of type 1, 0 and a form of type 0, 1. So any smooth one form can be decomposed as the sum of a form of type 1, 0 and the form of type 0, 1. And then star omega is defined as I omega 1 bar minus omega 2 bar. So we have this operation. There are some elementary properties. And then we introduced the scalar product. A scalar product. Suppose that now that X is compact. And we have two forms. Then we defined the scalar product as the integral over X omega 1 wedge star omega 2. And then we checked that it is indeed a scalar product. So what we checked? We checked that lambda omega 1 lambda also we proved that this is greater or equal to 0 and it is 0 if and only if omega is 0. This is all elementary. And the third property, actually, we did not check, but it's elementary, and I leave it as an exercise. This symmetry. Как это называется, если они меняются местами и сопрягаются? Как это называется? Не симметрия, как называется? Antisymmetry. No, it's not antisymmetry, it's omega conjugate. Is there a name for this? Okay, probably no. Yes. So this is exercise. Yeah, I will include it in the lecture notes, but yeah, it's elementary. Okay. Yes. And then what we have? We have a so as a conclusion, we have that this space of smooth one forms, is endowed with a scalar product. With a scalar. So the space of smooth one forms on a compact Riemann surface is endowed with a scalar product, and basically more or less everything is orthogonal to everything. More or less all the, if you're imagining some, we have natural subspaces here, and all of them basically orthogonal to each other. And this is the context of this lemma, of the following lemma. So yeah, basically d prime d double prime omega x omega bar x. So they are all subspaces here, and they are all pairwise orthogonal. So they are subspaces, and they are pairwise and also d this one and star d are pairwise orthogonal. Orthogonal. Oh, maybe I can just write. And d plus star d prime yes. So, but also I want to note here immediately that from this formula, it follows that this operation star, it moves forms of type 1, 0 to forms of type 0, 1. Yeah, because if you have 1, 0, type 1, 0, then you have only omega 1, so you take bar, you get 0, 1. And and back. And since star omega is equal to minus omega, then these are isomorphisms. So this is an isomorphism, and this is an isomorphism. Yes. Yeah, and then so maybe immediately after the definition of this scalar product, one can immediately make a remark that obviously 0 forms of type 0, 1 x are orthogonal to forms Here this is obvious because here what you have omega 2 is in, if omega 2 is in 0 1, then star omega 2 is in 1 0, and then here you take a form of type 1 0, wedge form of type 1 0, and this is 0. Yeah? So this is obvious. So if we want to prove lemma, then you see these guys are in 1 0 x, and these guys are in epsilon 0 1 x. Yeah. And so we know that they are pairwise orthogonal. So basically, if you want to, for number 1, only have to prove, we only have to prove that that d prime this orthogonal omega x, and d prime we only have to prove this, but actually the second one follows from the first one by taking bar, yeah, because yeah, basically yeah, so from here to here you take bar, and from so d prime d double prime from d prime yeah, e of x to d double prime e of x, you also take bar. This is d prime and here also, I mean, you can take a bar, and this is so what you have bar. Star with bar. They commute. Yeah. So star to bar is equal to star. So we discussed this property. So in particular, again, some remark, maybe second remark. This is, but also you have that omega 1 bar, omega 2 bar is equal to omega 1, omega 2 bar. Yeah? Yeah. So basically, the second property follows from the first one. And yeah, the first orthogonality is easy. What you do, you just apply Stokes theorem. You just write integral over x d prime some function wedge star omega, where omega is holomorphic. Yes. And then you can replace d prime by d. Yes, df. Yeah, because you can add d double prime, but this will not give any contribution because star omega is of type 0 1. So if you add d double prime, then it will also add a form of type 0, 1. And then this will not give any contribution. So you can replace d prime by d here. And also here I claim that this is equal to integral d f star omega. Yes, but yeah, this is just this is because d star omega is equal to 0. And this we discussed, yes? So we actually discussed that this is anti-holomorphic form. Star of holomorphic is anti-holomorphic, and d of anti-holomorphic is 0. So we have this, and so by Stokes' theorem, this is 0. Yeah, so this is part 1. Do you have any questions? No. Okay. Yeah, and then the second one is also easy. Maybe I leave. Maybe I leave here this definition of star operator. By the way, indeed, there was some remark at the end of the previous lecture that there is another star operator in the theory of complex manifolds. There is this Hodge operator, also denoted by star. But it's not. I mean, it is this Hodge operator is not related to this in an obvious way, because I mean, this Hodge operator depends on the metric. And, it looks like they are not related in an easy way.
Sorry, again, the last step was Stokes, right?
Yes, Stokes.
But then the exits changed to the
Boundary.
boundary.
But no boundary. We don't have. We have compact Riemann surface, no boundary. Yes, and then we want to prove number 2. Number 2. So you just compute df and star df. Okay, by definition, integral over x df wedge star dg. Two functions. dg. And then, this guy is minus dg. And so this is equal to minus integral d f wedge dg. And again, by Stokes' theorem, this is 0. Yes. Yeah, and then yes, and then you so we have proved the orthogonality. Yeah, then we want to prove this equality, but yeah, this is just elementary computation. You just write that. Yeah, so obviously, d plus star d, it is included in d prime d double prime here I missed E of x. But so obviously we have this one, but we also have another inclusion. Because you can express d prime of any function. Trivial linear algebra. df plus I star df bar over 2. And d is df minus I star df bar over 2. Since d prime of f and d double prime of f can be expressed in terms of d of something and star d of something, then this implies another inclusion. Okay, any questions? No. Okay. So in particular, so in particular, so you see d prime, so in particular d, this space is orthogonal both to holomorphic and anti-holomorphic forms. But the sum of these guys is the space of harmonic forms. So we get the corollary that corollary that harmonic forms is orthogonal to d just because these harmonic forms is the sum of holomorphic and anti-holomorphic. Okay. Yes, then what? Yes, and corollary. Then we have theorem saying that the forms of type 0, 1, this space is the sum of d double prime direct sum forms of type 0, 1 is the direct sum of d double prime u of x plus anti-holomorphic forms. Yeah, maybe I indeed, yeah. So we have three statements. Actually, a conjugation of this equals d prime plus holomorphic. Yes. Yeah, and we also have the decomposition of the space of all forms. It's star d plus harmonic forms. Yeah, so yeah, so basically the only non-trivial part is part 1, because from 1 we have 2 just conjugation by just by conjugation. Yeah, so if when we take bar, then we obtain from 0, 1 forms of type 1, 0. Yeah, from d double prime we get d prime, yeah, and then from this we get this. So this is conjugation. Yeah, and then from 2 we get 3, just because just because harmonic forms is the sum of holomorphic and anti-holomorphic, and this star d e plus de is equal to d prime e plus d double prime e, as we have just proved. And this, yeah, the sum of forms of type 1, 0 and forms of type 0, 1 is the whole space of smooth forms. So this is obvious. So it remains to prove one. But one we basically what we actually we already more or less we considered. Okay, so we have a short exact sequence. What we have? We have what should we write? Ah, yes. So we have epsilon. The following short exact sequence of sheaves on X. So we have 0, locally constant functions. Locally constant functions are included in the space of all smooth functions. And then you apply d double prime and obtain forms of type 0, 1. And so you have holomorphic forms. They are included in all smooth forms. Then you apply d double prime and get forms of type 0, 1. This is and it is exact. Here it is obvious, just inclusion. Here it is also obvious. If a function is holomorphic, if only d double prime is 0. And the fact that it is exact here is less trivial. There was some lemma saying that locally any form of type 0, 1 is d double prime of some function. So the exactness here was some theorem. And then you write long exact cohomology sequence. So you obtain long exact sequence of cohomology groups. Here or 0? This here 0.
No, the second from left.
It's O, holomorphic. So O, calligraphic O. So yeah, holomorphic. So sheaf of holomorphic functions. Yes, and then you write a part of the long exact sequence of cohomology groups. So you write E of x goes to E01 of x, and then you apply this connecting homomorphism delta. How we write it usually? Okay, anyway. H1 x O. And then we know, again in the spring course, we proved that H1 of E is 0. So 0. And then, so this means that this map is surjective. So is surjection. So the last map, this one, is surjection. And the image is isomorphic to E01 of x quotient by the image of D double prime. So H1 XO is isomorphic to E01x quotient by D double prime EX. Yes. Yeah, so, but yeah, so, but we know that, by definition, yeah, dimension of H1 is equal to the genius. Yes, so, but we also, so you see, D double prime of E is a subspace here. Yeah, and we know that antiholomorphic forms are orthogonal. So dimension of 0, 1 x quotient. So we have obtained that this dimension of the quotient is G. Yeah. Then we also know that omega bar x is orthogonal to D double prime E of x. And we also know that the dimension of this guy is also G. And so these facts, they imply that actually, yeah, so if you take the sum of these two guys, then you get the whole space. this is equal to d double prime yeah. Okay. Okay. So you see, at the moment everything is quite elementary. So this completes the proof. And yeah, another simple theorem. It says that if you consider the space of all smooth forms, so you have all smooth forms, you can apply D and get forms, get two forms, then the kernel is equal to D E of x plus harmonic forms. Yeah, again, this is elementary computation. Yeah, we know, we already know that the space of all smooth one forms has this decomposition: star D plus harmonic forms. And clearly, if you apply D to D, you get 0, and if you apply D to harmonic, you get 0. So clearly, we already have it. That D so let us so this sum is in the kernel. Let us denote this kernel. This kernel by L. So this sum is in the kernel. And then, if you want to prove that the kernel is equal to this guy, it is sufficient to prove that the kernel is orthogonal to this one. So it is sufficient to prove that star D is orthogonal to the kernel. But this is a direct computation. So what you do, you take some function, what you do. Yeah, so let us take some function here, f, and some form omega. Yes, and then let us then compute omega, the scalar product of omega and star df. This is equal to integral over x omega wedge double star df. This is equal to minus integral omega wedge df. And then you can write this is the integral d omega wedge f. And here you use that omega is in the kernel, because d of omega is 0. So you can then omega wedge df is equal to d omega wedge f. And then this is 0 again by Stokes theorem. Any questions? Okay. And then we have just this what we have just done. It computes allows to compute the ramp homology groups. Yeah. So recall that if X is a smooth manifold, then we have the Durham homology groups. Yeah, then I think I denoted them in this way. Then this is equal to the kernel of the map D from of the map from forms of type from n forms to n plus 1 forms over the image so this is the RAM homology groups. The RAM homology groups. Yes, in the spring course, actually, we introduced it in the spring course. And also, we know that H1, the RAM X, is isomorphic to H1 XC. So these are locally constant. I mean,